So it's either you are given something like this, a map that has the following information. So it must show you the length of the pipe or the corridor of the drainage. It must have elevation points, beginning and ending. So shortly, I'll give us a case study. I'll show us an example of a detailed, well-detailed design. I will relate with what I'm saying. Then you must be able to understand, to know the length of each section. It could be 10 meters, it could be 5 meters, depending on what the job the surveyor have done. So the end and the end point, the starting and the end node must have elevation value. From there, you can get your slope, because slope is an important component in sewer and stormwater design. So slope is vertical over horizontal. Remember our Pythagoras. The distance between 2 points, the elevation difference between the 2 points divided by the length give you the slope. So the slope helps you to do your pipe sizing. With the slope and the discharge, you can size any pipe, of course, considering the roughness of the material or the frictional factor. Then the area of the catchment, the catchment area that network, that pipe is serving. Okay, like in a street now, I think just I showed us an example where any pipe passing along the street will be serving both catchments of the street. So what is the first thing we do on the part of the sewer, or on the part of the storm? We did catchment characterization. What is the coefficient of the runoff from the whole catchment? And to do that, we calculated what is the area covered by green gardens and parks, what is the area covered by streets, what is the area covered by roads, and what are the other areas. Then you estimate their corresponding coefficient of runoff. In other words, to what extent do they contribute to runoff? To what extent are they paved? To what extent are they pervious or impervious? Because the ones that are impervious are the ones that are contributing to runoff. Even when they are impervious, there's a degree of their paving, and that is what culminates into establishing your runoff coefficients. Then the other parameters you need to establish is to say, what is my design storm? Is it 10 minutes? Is it 15 minutes? I told us yesterday, in Germany, they use 10 minutes. Here in Nigeria, we use between 10 minutes and 15 minutes, but anything beyond 15 minutes does not contribute to maximum runoff. Does not contribute to maximum runoff. Then the next thing you do for the purpose of sewer, so the two parameters you need for storm is your runoff coefficient and the area, so that you can get the effective area contributing to runoff. In the case of sewer design, still on storm, you do the runoff and then you establish your storm parameters. In other words, area parameters, which is the area and the runoff coefficient, which is a function of the imperviousness. And then the next thing is the characteristics of the storm. How intense is the storm? How many minutes is the storm? And what is the frequency of the storm? And what design storm am I using? So those two parameters is what you need. Then you go to the rational table and you start to do your calculation. In the case of the sewer, you are interested in the water demand consumption, because this is what we call anthropogenic activity that relates with human activity, anthropogenic. So garbage in is garbage out. If you remember the law of continuity in thermodynamics, what you consume is what you produce. So in countries like Germany, once they are giving you water, they are charging you for wastewater. So 1 cubic meter of water in Germany is about 2.25 euro. So they will charge you 5 euro, meaning that they expect that what I'm giving you as drinking water, after using it, I'm still going to collect it as wastewater. So the input parameter is the water consumption, the water usage, the water demand. They all mean the same thing. Those words can be used interchangeably. Then the next thing is the population density, because the units, when you get, let's say there are 1,000 people, and one person consumes 130 liters per capita per day, it means that means the total number of flow that you get will now be 1,000 people multiplied by the specific or the unit water consumption. Then the other thing you do is you multiply by a safety factor. One of the prominent things in infrastructure design is the use of safety factor. Even in dams, sometimes when you design your dams against overturning, you multiply by 2 or 2.5, depending on the return period of the flood you're using for your design. So the same thing applies in infrastructure design. We design based on futuristic projections. Don't design based on now. Next week, when we're doing the water reticulation design training, you'll find out that you need to define how long you want this design to last. If it's 60 years, then it's expected that after 50 years, the design will reach its lifespan. So the population you're using will be the population of 50 years, not the population of today. So the same thing applies in sewer design. So that is why we decided to multiply by a safety factor of 2. Now, something guides this safety factor. Just don't pick safety factor for picking sake. Part of what guides it is the population equivalent you are designing for, the number of persons you are designing for. The higher the number, the smaller the safety factor. The smaller the number, the higher the safety. Sorry, the higher the number, the smaller the safety factor. So if I'm designing for 1 million people, you use a higher number. If you're designing for less than 1 million people, you tend towards 2 or 2.3. But most times, the population, the safety factor is no more than 2.5. In German standard, it's about 2.3. But if you read the highway manual, you get the standard for Nigeria. Then the next thing is that you determine what we call parasite water. This parasite water is just for you to make an assumption of, say, there might be seepage, there might be infiltration water entering my sewer line. So you need to take care of it. Or there might be strange water coming from wherever that might be included that I need to design for also. Okay. So then, of course, the pipe roughness. Are you using PVC pipe? Are you using concrete pipe? Are you using asbestos ceiling? Are you using ductile iron? All of them have their own coefficients of the roughness. Okay. Then the next thing is when you have gathered this parameter, the universal pipe sizing method is to use discharge, slope, and roughness. Discharge, slope, and roughness. With that, you do your pipe sizing. Then the next thing you do before you do your, before you do your storm, you need to determine 2 things. Good. Okay. After you have gotten those values, the next thing you do is you estimate your unit flow based on area. So for the sewer, we don't know the population, but we know the area. And we are giving that the population, we are giving the population density. Population density is that when the design is finally done, there is going to be 100 people per hectare. Remember, 1 hectare is 10,000 square meters. So that translates to 10 people per 1,000 square meters. And that could be like a 4-bedroom duplex, 10 persons per plot. So now you are giving the land use, or you are giving the population density, you can convert both of them interchangeably. So then what I need to do now is determine what is the quantity of wastewater flowing per hectare. And it is gotten by saying the water demand or the wastewater flow multiply by the number of persons per hectare. Then this A6400 is a conversion factor. What are we converting? We are converting daily to seconds. This 130 is given to you in liters per seconds, liter per capita per day. But in pipe design, we design pipe based on liter per seconds. And that is the minutest unit, liter per second. Take note of that. Take note of that. Liter per second. That's the unit you want to get. So we multiply by 2, which is our safety factor. Multiply by, add the safety factor for infiltration. at the end of the day, we got 0.401 liters. So it means, this value means that for every 1 hectare, the flow of wastewater will be 0.401 liters. So if there are now 100 hectares, if you multiply by this, you will now get your answer in liter per second. And that becomes your discharge. That becomes your discharge. Okay, so 0.401 is now the unit flow per hectare. So we are still going to leave it in liter per second per hectare, so that when we get to any area, we just multiply this value by the area, we will now get the unit discharge coming from that area. That will eliminate the hectare, and we'll now get our liter per second. Any question? I want that to sink in. I want it to sink in. Okay, let's come to storm. For the storm, what do you do? Very simple. Multiply the area. I told us yesterday about, see, engineering is universal and it's very wonderful. The universal formula for discharge, anywhere you go, any textbook you go, is always area multiplied by velocity. Area multiplied by small q is the same thing. Some people in some schools or NUC will do it as CIA, where I is equal to velocity. When I say millimeter per hour, rain intensity, that is a function of velocity. Yes, millimeter per hour. So you just have to convert it to meter per second. And then multiply by the area, you get your meter cube per second. And that becomes your discharge. That becomes your discharge. So our interest is to get the discharge. In any pipe design, your problem is, what discharge am I trying to convey? What discharge am I trying to take out of the catchment? Then what is the pipe size that will take out this number of discharge per second out of that catchment? That is what it is. So when we say sewer design, stormwater design, what are you really designing? It's the pipe. It's to size it. It's to size the drain. Whether you're using open channel, you're using pipe, or you're using a trapezoidal channel, or you're using whatever mechanism you're using. It's just your discharge is your major input parameters. But then to aid you and to get it well, you now need to find out the slope also, because the higher the slope, the higher the discharge. And of course, you also find out the roughness of the materials you're using, because the roughness also impedes flow based on Euler equations. Euler tells us that as water is flowing in the pipe, it is having three contacts. It is flowing in 3 dimensions. It's having an interaction with the body of the material. It has turbulence or momentum, and then it has normal laminar flow or velocity. Okay. So for the case of stormwater design, the 2 input parameter is your rain intensity and the catchment area that this rain intensity is falling on. So that is what you have here. But in getting your rain intensity, the rain intensity must be a function of the duration and the frequency. Okay, the duration must be 10 minutes or 15 minutes from what we said, and then the frequency is a function, or is a political decision, the decision of what you are designing against. Is it against surcharge? Is it against flooding? Is it against ponding? So we also say that you break this A to arrive at this A, you need to multiply the catchment area multiplied by the coefficient of runoff, or the peak runoff coefficient. So down, frequency, return frequency depends on the associated risk with an overloading. Now we talked about design frequency, your defined frequency. Which one do you use? 5 years, 2 years, 10 years, 25 years? We are not telling you that the one you use will depend on the risk In other words, are you designing for storm? That's the first one. Are you designing for surcharge? Or are you designing against flooding? It is rare to design against flooding. It is only in exceptional case that some places in Lagos are flooded or some places in Abuja, then the authorities will now say, let's design this place against flooding. And that is when you start seeing massive, like in Asaba. My friend that did a design for Asaba. Okay, Asaba design is against flooding because Asaba have been flooding and now they move to Warri. It's been flooding. So when you are doing that kind of design, you'll be using frequency of 10, 20, 30, 50 years. But when you are designing for a normal estate, a normal district, without any anticipation of flooding, and the risk, and that place is like a rural area, you use 1 year. If the place is a highly density, highly residential area, you use 2 years. If the place is a city center, like central area, or like Ikoyi, or like which other place, or like Hybro area, Ikoyi or VI, then you use like 5 years. Then if you are designing for special areas like underground railway, underground subways, where the risk of flooding is dangerous, is high, where the risk, the insurance risk of flooding is very high, where event of risk of flooding will cause massive devastation of property, then you use a higher return period. And that's why here, even for next storm, you're using 10 years. For flooding, you're going to use 50 years. So if I want to protect Ikoyi against flooding, I'll be using the design frequency, storm frequency of 50 years. Because in the event that Ikoyi floods, there's a massive risk associated with it. Okay, so here it says, once again, how do you choose your D and N? So the next chart now will tell us how do we choose we have chosen N, we have chosen D. So D is chosen in the range of short events, 5 to 2 minutes to 2 hours. The duration has an extremely high influence on the rainfall. So why do we choose D of 10 minutes or 15 minutes? Because as engineers, we design for worst case scenario. What is the worst thing that can happen? Even in those of us that are structural engineers, when you are doing your loading, you don't use the minimal loading, you use the maximum loading. Even though you also use the minimal loading just to be able to derive the optimized loading. But then your focus will be on the minimum, on the optimal loading. What's the worst thing that can happen? What's the maximum load that can come upon this structure? So the same thing happens. So we know that the highest storm event occurs at 10 minutes or 15 minutes, where the duration of the fall is equal to the time of flow. Okay, so I think I've emphasized this so much. So I've talked about this again, that why do you need to multiply area and the coefficient of runoff to get your impervious area? The reason is that it is not every rain that generates runoff. Sometimes it could be 30%, 40%, 50%, 60%, but it has never been 100%. The reason being that some storm events will go to wet, they will wet the ground. Some will drift away. Some will evapotranspirate. Some will infiltrate and meet the groundwater. Some will go into depression storage. Then finally, a small portion will come out as surface runoff. The other events that the runoff also occur, why is also the slope. So here also gives us, this is German guideline, DVR A1180. This is the one we use when we're doing this course. So it says that if the slope of the area is less than 1% and the degree of paving is less than 50%, you should choose 15 minutes or 10 minutes. You should use between 15 and 10 minutes, but 10 minutes is recommended. If the slope of the area is between 1% and 4%, that means the place is very steep, you should use 10 minutes. Now, if the slope is greater than 4%, and the degree of paving or the impervious area is less than 50%, you should still use 10 minutes. But if the degree of paving is so much and I made the paving is more than 50%, you should use 5 minutes. But I want to tell you this, forget about 5 minutes. The minimum you should use is 10 minutes. So based on these three conditions, you can see that 10 minutes is more pronounced. It's only when the place is almost like a flat land, and the degree of paving is less than 50%. That is when you can use 15 minutes. In other words, it will take a longer time for rain that falls at the beginning of the gate to get to the end of the drain and contribute to flood or to contribute to surface runoff. Because when the land is flat, there's every tendency that a lot of water will percolate before it will flow. And when there is much percolation, when the hydraulic conductivity of the ground is very good, then there's a likelihood that runoff will be small. That's why if you go to developed countries and some districts, they are interested in having green areas, making sure that there are enough green areas. These green areas serve as infiltration basins for stormwater. So you limit the quantity of water that flow into the drain. So here, this is an example. At rain of 10 minutes, return period of 1 year, the rain intensity runoff is about 126 liters per second per hectare. He said if flow time is longer than 10 minutes, only part of the catchment produces runoff. You see it. So if the flow time is too high, that's why Lagos rain, sorry, this might not be accurate, but you know, Lagos rain sometimes, it will rain the whole day in Lagos, yet there's no flooding. Here in Abuja, it can rain for 5 hours. You won't see flooding, but you will see some rain that will rain for just 30 minutes, like the one that rained last week or this week. 2 hours, 1 hour. But because of high intensity, it will generate flood. So it's not a question of the duration of the rain that causes flooding. No, it's rather a function of the intensity. In fact, the intensity and then the slope of the area, the higher the slope, the more it can contribute to runoff. And then the return frequency of that flood. So what are the steps we're going to take when we're doing our storm design? The first thing is you determine your return frequency, you estimate your time of flow. Time of flow. Remember in our physics in secondary school, velocity is distance over time. Velocity is distance over time. So if the thing is coming at 100 meters and the velocity is 2 meters per second, then means the flow time will be about 50 minutes. Well, just do the calculation. 50 seconds, sorry. So now consult IDF. Yeah, 50 seconds because velocity is in meters per second and the distance is in meters. So you consult your IDF curve to get your corresponding rain intensity, which is influenced by the duration and the frequency. Then you calculate your wet weather flow. That's for the sewer. For the sewer, you calculate your wet weather flow. Okay. Then you choose adequate pipe diameter, considering the security factor. Required diameter depends on the discharge, the slope, and the roughness. The discharge, the slope, and the roughness. Okay. So the next thing now, after that, is to look at the degree of filling. This is not important. So after that, after you have consulted, well, number 5, these are the steps. Choose an adequate pipe diameter, considering security factor. Then after that, you consult your table to get your real velocity. Then you calculate your flow time. Then you compare the results to estimation. Now, from number 6 to number 9, these are what we call check. When you have done estimation, which we always do in engineering, you now go back and validate your assumptions to see whether they are real. So you now check your dry weather conditions. All these ones are academics. They're not too important. Our job stops at number 5. And once we get to number 5, we go to our detailing. We go to AutoCAD and detail it. And how does the detail look like? Let me just show us one thing, one job. Documents. Just stay with me. Okay. So let me just show us let me just show us how the detailing look like, because detailing is another component. Okay. Good. Okay. I don't know if you can see my screen. Okay. Let me zoom in. Just hold on. Good. So after you have gotten your value, you now come and detail your work. For every drain, this is like pipe 17, catchment 7. I will explain this. This is just like our those of us that are civil engineers, our BS detailing. This is 0.02. This is the slope, and then this is the type of drain to be provided. And what is that type? Is a trapezoidal member. After you have gotten your cross section, you now determine which type of drain you want to use. Is it a circular member? Is it a rectangular member? Is it a trapezoidal member? I showed us many different shapes, but our emphasis is to get a cross section. So in this case, this is a trapezoidal member. Trapezoidum have the bottom length, the side length, the depth, and the top. I'll still come to that, but I just want to show us, after you have gotten your thing, this is how you now label your detail your drawing. So let us continue. Let's finish the calculation first. The calculation sheet. So yesterday I tried to explain to us yesterday. Let's take, for instance, this is pipe A, catchment A. I will come here, I'll write pipe A. Pipe A is starting at this and it ending at 2.2. The area of this catchment is this. And the flow, the wastewater flow, how do you get the wastewater flow? The wastewater flow is you multiply.
It's like your screen is not showing.
Sorry. Okay. So how do you get the wastewater flow? From our chart yesterday, the wastewater flow is it's gotten in liters per second, and that would be your. We got it here. Just hold on. These are wastewater flow. The water demand per person multiplied by the population density, convert it to seconds, multiply by the safety factor, and then add the infiltration water. Let me demonstrate it with whiteboard. We said this is discharge. So it means for residential area, for instance, for storm, for instance, Q, for sewer, for storm, let's start with storm. For storm, the area will now be my catchment area. Multiply by the rain intensity. Okay, catchment area multiplied by rain intensity. That will give my discharge. But this catchment area is there are two variables. And those variables are the catchment area multiplied by the runoff coefficient. Remember, Okay. Then the rain intensity now, how do you read it up? You read it based on the return period. And I'm not supposed to say multiply. And the duration. These two will tell you how intense the flood is. Good. I don't know if this is making sense. This is equal to A multiplied by Q. So A multiplied by Q is the catchment area, which is a function of the area and the runoff coefficient multiplied by the flow or the velocity of flow, which is now a function of the rain intensity, return period, and duration. So that is what we got here. Well, here. So this is how you got it now. So here, wastewater demand multiplied by the population density, multiplied by the safety factor, add up to infiltration in water. It will give you 0.41. So when you say 0.41, multiply by the area. So let's do that quickly. So for the first one, the area is 15.5663 hectares. And the wastewater flow, let me call it small q, is 0.401 liters per seconds per hectare. So if I now multiply 15.63 multiplied by 0.401, it will eliminate the hectare. So that will eliminate, sorry. So if you multiply this, I want to do this quickly. Where's my phone? Okay. So if we do this quickly, 15.63 multiplied by 0.401, it will give me 6.26. So that is how we got the first here, 6.26 for the wastewater. So I put it down, 6.26. I'll go to catchment B. Stay with me. I'll go to catchment B. Sorry. Yes, I'll go to catchment B. Catchment B is upstream, is downstream of catchment A. So I will calculate the flow for catchment B. I will now add it to the flow from catchment A. So when you come to this table now, what you see here is that for catchment B, it is, the area is 5.43. The area is 5.47. And we multiply 5.47 by 0.401. Let me quickly do that one again. So catchment B here is, please, let me say this. Can we all open these charts? Because I'm moving from my whiteboard. I keep moving from whiteboard to screen sharing. But if you open your chart of fractional method, can we open this chart so that I want to show us how to use this chart? Once I get that done, it makes the work easier. Please. It makes the work easier. So here, with the sanitary sewer, which we started, we have done this first one, we got this. We did the second one. Catchment area multiplied by the runoff. We got 2.19. Yeah, we got 2.19. But the accumulation will now be what we got for catchment A plus the value for catchment B will now give us the value for catchment B. In other words, what are we saying here? The wastewater flow here will flow, people are living here now, they will contribute their own wastewater flow here. This water flow now will flow to the next catchment. Those of you that are conversant with Abuja, the wastewater flow coming to Maitama will come to Wuse and join the wastewater flow from Wuse and then go to Wuye. No, Wuye. Go to Jahi. Is that the route? Yeah. From Jahi, it will join the wastewater flow from Jahi. Then it will go to Life Camp. It will join the wastewater flow from Life. So as it is going towards Whooper treatment plants, it will be accumulating. And how does it accumulate? Because this person will generate waste. That waste will flow into this person. So it will accumulate. And that is what people have challenges when designing some of these pipe systems. You need to know which one is downstream and which one is upstream, so that you know that the person upstream will contribute to the person downstream. So when you come here now, you see that catchment A, its own sanitary wastewater, its own wastewater flow is 6.62, which we got by multiplying the unit wastewater flow by the area. Then the person for B is 2.19 because B has a smaller catchment. This is B. And A has 6.26. But the wastewater flow at this point will now be the one for A plus the one for B. Please, do you understand it? If you don't, you can hear me. So the total wastewater flow here now will now be this plus this will now give you this. When we get to C, this is C. C is independent of A. So the wastewater flow for C will now be absolutely C. So this is C. This is the catchment area multiplied by the unit wastewater flow. It will give you 5.64. So the total flow in C will remain 5.64. While the total flow in B is what? 8.46, because you are aggregating the one for A and the one for B, because B is on the part of A. It's on the flow line of A. So the catchment A need to meet catchment B before going forward. Then when you come to D, you find out that D is having 3 catchments upstream. And what are those catchments? Catchment A, catchment B, and catchment C. So the wastewater flow here would now be A plus B plus C, because he is on the downstream. We are assuming that wastewater treatment plant is located here for the sanitary sewer. That's our assumption. Well, or if it's for the storm, it means there's a river here, or a discharge point, or outfall is here. In the case of sanitary sewer, treatment plant is here, or cesspool, or septic tank, something that will convey the waste, or treat the waste, sorry, is somewhere here. So it means as this man is flowing, it will enter B, then C will also join them. So when you come to this table, that is why you find out that under D, the absolute wastewater contribution or absolute wastewater demand of D is actually 1.57, because it's a small catchment. But the total wastewater flow at that point is about 15.066. Why? Because D is now A plus B plus C equal to D.
I'm attending a conference.
If you don't understand it, you let me know. So D is now A plus B plus C plus itself. We give you 15. Because its catchment D is contributing 1.57 in wastewater flow. But the pipe at that point is taking wastewater flow coming from A, coming from B, coming from C. So total wastewater flow at point D is 15 liters per second. 15 liters per second. Because he is carrying the load capacity of the 3 catchment upstream. So all of them are emptying into him. Now the question is, what will be the value for E? The value for E will just be only the catchment of E. So for E, what do you have there? E is just 5.95. E is the catchment area multiplied by 0.401, which is the wastewater flow per unit hectare. It will give us 5.95. Why? Because D is the last catchment. It does not have any tributary. It does not have any layout upstream. It does not have any catchment upstream. So it's only contributing itself. And that is why you have it here. E, sorry. So how about F? Take a look at F. I'll ask the question now. How many catchments are contributing to F? Can somebody answer? You can unmute yourself. How many catchments are contributing to F? I want an answer. If you cannot answer verbally, put in the chat box. How many catchments are contributing to F?
You have catchment A, B, C, D, E, and F itself.
God bless you.
It's going to.
Thank you. And that's why when you're laying the pipe for catchment F, you find out that it will not be the same size with catchment A. It will not be the same size with catchment B. It will not be the same size with catchment D, because the pipe size at that point will be bigger than the pipe size at B and far, far bigger than the pipe size at C, because it is the one downstream. So how about catchment G?
Catchment G is only catchment G.
Thank you. How about catchment H?
Catchment H is everything all together.
Thank you. So if we now go to the chart now, you see that as the wastewater is getting towards the treatment plants or the point of conveyance, is increasing in flow. The flow is increasing. That's why if we see some design, I've seen some design, people will use the same pipe size and I will laugh. It's not possible. Some people will just come to estate design, they'll say, provide 4 inches pipe, provide 3 inches pipe everywhere. No, you need to check where is the water coming from and who is contributing. What are the tributaries that are coming? So if you get those contributions, then you will now be able to know how the pipe size is gradating with time, how it's increasing.
Sorry, can I quickly ask you this question?
Go ahead, sir.
Now, this small q subscript DW meter per second, where do we get that from? How do you assume that? How do you get that?
This column number 5.
4. Sorry, 5.
5. Okay. Column number 5 is that the first thing we did is to say, what is the wastewater flow per hectare? Since we are dealing on catchment basis, we are not giving number of houses. So we're just giving the population density. The population density is 100 persons per hectare. So we now say, yeah, this is how we got it. So how we got it is to say, we are looking for the small q. If you multiply small q with the area, you get your q. If you multiply the velocity or the unit flow. So 130 multiplied by 100, which is the density per hectare, convert it to liter per second by dividing it by A6400. This A6400 is
Hello?
Yes?
This 130 is the water demand.
Yeah.
Okay.
We discussed yesterday, you choose between 100 and 250. In Germany, they are using 120. In Nigeria, they're using 100. But at the end of the day, you still have to multiply by a safety factor. Like Abuja, when they designed Abuja, they use 100 liters per person per day. But they multiply by 2.3, which is safety factor for 1 million people. Abuja was originally designed for 1 million people. I don't know what the number is now. So this is how you got. So the only thing that is missing in this formula would have been to tell you the number of houses, number of persons. But this Hectare has taken care of it. And that's why our final unit is in liters per seconds per hectare instead of liter per seconds. So what we now need to do is to multiply by the corresponding area. And that is what they did here in column 5.
What is this PD? Hello, you are still
PD is the population density.
Population density.
Yes. Population density is 100 capita per hectare. And that's for low density. That's for low density. Yes, that's for low density. You know, when you come to meeting, you know, when you are given a layout that has houses, you can start saying this is 4-bedroom house, it has 20 people inside, this is 3-bedroom, it has 20 people inside. So number of houses is 100 multiplied by 10, you give you one. But now it's like a virgin layout. So you don't know number of persons, but you are given a guide. And that guide is what we call land use. That's what we have what we call land use act. If you go to every authority, they're supposed to, if you are given a district design, they should give you the land use to tell you this is a medium density area, this is a high density area, this is a super high density area.
Yes.
So with that, you now multiply that. You now do, as engineers, you now know, say, every 1 hectare, what is the quantity of sanitary flow coming out? And that is 6. That is 0.401. That's what we got here.
Hello, are you with me?
I'm with you.
This population density now, you know, I know that in the land use, it will be indicated which one is the density of the plots. Yes. But what's the reference for what quantity of per capita you're supposed to expect on? Is it low, medium, or what do you call it? What's the reference? Where do I get that?
Your client will tell you, like, let me just give you instance. One of the design I did last time was this place around Kakurudu. They call it Gidamango. If you're going to Karishi. So they designed that place as medium density. They designed that medium density, though they didn't do the sewer design, but that place is like a medium density. So they'll be giving you like between 300 to 500 capita per hectare.
300 to 500.
Yes. So these values are established by authority. So in Abuja, I think it's FCDA or FCTA that establishes that. You cannot, the value for Germany, Italy, they're all different. If you go to the US, there are about 50 of them. The 50 states have their own. So if you want to do a design, there are some values or there are some baseline that will be given to you by your clients. So what is in event that your client doesn't give you those baseline, you will now ask questions and establish your own, make assumptions, but then reasonable assumptions. Let me give you one example. Let me do one demo now for you to justify what it is. Some of these estates we build in Abuja. Let me just give you one typical example. 1 hectare. Let's use 1 hectare now. Now, just hold on. This will be 1 hectare is equal to 10,000 square meters, right? One thing I know in Abuja is that most of their land is 500 meters or 500 square meters. Most of them, they give you land for 500 square meters, and they expect you to build a 3-bedroom bungalow. Just watch me, stay with me. 3-bedroom flat in every 500 meters. Now, let me tell you the density they are using here now. Oh, first, each 3-bedroom let's assume there are 10 people, 10 persons. Somebody will argue 8, but don't worry, use 10. Always use the higher worst case scenario. Each 3-bedroom. So the question is, what is the land use? So most estate developers in this Kuje, Lube, all these aspects, this is normally their baseline. So now the question now is, what is the land use? How many plots will be in 10,000 square meters? That will be 10,000 divided by 500. What would that give you? 10,000 divided by 500. That will give you 20. Am I right? So that will give you 20 plots. So that means for one hectare of land, if you divide it into 500 square meters, it means you're going to get 20 plots in our layman's language, 20 plots, yeah. But we said that each plot we expect you to build 3-bedroom duplex, and that 3-bedroom duplex will accommodate 10 people. It means that the land use of this area is 200, will be 20 multiplied by 10, which is equal to what? 200. Please, I need one. So that will be 200. Eh? So it means 200 capital per hectare. So that's the land use. So instead of me giving you all these things, you say, if it's not an estate that the architect, they have done the layout and mark out 500 meters, and I can plot, I can count the plot. All my clients need to tell me is to say, please, engineer, design this place as low density area. And the low density area in their manual is 200 capital per hectare. So instead of now, so when I now go to calculate my wastewater discharge, my wastewater discharge will now be the population equivalent, as we usually do in water design, multiply, that is the population equivalent multiplied by the unit wastewater discharge. So what changes now is what? Population equivalent now is now going to be what? 200 per hectare multiplied by 130. Then other things are multiplying are safety factor, multiply by safety factor of 2, multiply by add infiltration coefficient. These are just standards, normal standards. Now, this 200 is in hectare. So my answer will not be liter per second. My answer will not be liter per second per hectare. So if this thing now is no longer 1 hectare and they say it's for 10 hectare, it means whatever value I get here, multiply by 10. Like here now, this is the 1 hectare is 200 persons. So 10 hectares is going to 0.1 is, we said 0.1 is a factor of safety to take care of infiltration water.
Are you supposed to multiply it or to add it?
I add it. I add it to whatever I get here. And what I'm going to get here is going to be very small.
The 130 is the water
wastewater contribution per person. Yes.
Okay.
Yes.
And then the 2 what?
Is factor of safety, peak factor. It's a peak factor.
So 2 plus 0.1 is the factor of safety.
There are 2 factors of safety. Sometimes when you talk about factor of safety, factor of safety for this, for overturning, for this. So for in this case now, we have factor of safety for infiltration water. We now have factor of safety for these 2 factors of safety is a standard. This is the factor of safety that takes care of many things about your demand, which could include wastage, leakages. Where the factor of safety comes in is in water reticulation, in potable water. When you use 2, it takes care of your peak demand. It takes care of your, there are many factors, but it's just a standard. Let me just use that word, it's a standard. Okay. So the all what we are trying to say is to explain how this table came about, because it's important that we got how this table came about, so that our end value is to get these pipe sizes. Once you get these discharges, once you get these discharges, you now move to your pipe sizing, which is here. You move to your pipe sizing. So let's continue. So back to the storm. So these are the steps we said you follow. You choose your frequency, or in case of the storm, time of flow, consult your IDF, calculate your wastewater flow, and then you choose the adequate pipe diameter. So here, this is the area. This is the discharge.
You can see what you're talking about.
Okay, sorry. So for the wastewater design, we're going to do this shortly now. For catchment A now, this is the area of catchment. Then multiply it by the unit wastewater flow. It will be, let's multiply this 15.63 by that 0.401. Multiply by this. Multiply this, it will eliminate the area, and you get your answer in liter per seconds. And that is the value.
This Q subscript INF, what is that?
Okay, that's infiltration, the 0.1. This shouldn't be a problem for us. This thing is just is a standard. This is the flow that takes care of infiltration water.
Hello.
Yes.
Okay, let me come in here. This that QE, that Q inflow. If you are using the software, if they will be using the software tomorrow, so you will come across. Hello, can you hear me?
Yes.
Okay, you will come across something tomorrow that is called RODII, which is rainfall RODII, which is called rainfall dependent inflow and infiltration. So that factor, that I, those double I, one is for inflow, one is for infiltrations. So those are the factors you are saying. When rainfall, because of the seawall, because of the sanitary seawall, some inflow will be infiltrating into the pipes, and some will be coming from runoff. Because of the runoff, they will be infiltrating also into the pipe. To avoid overloading the pipe, you will consider a factor for inflow, you will consider a factor for infiltration. So that is the RODII. So those are the factors you are saying. That one is for the infiltration, and the other one is for the inflow. So tomorrow, okay, when you will be using the software, you will be seeing the something inside it.
What is small f?
That is the factor for inflow.
That's a small f.
Yeah, for inflow.
Okay.
Yeah.
Okay, thank you, Sunday. Just to add to what Sunday said, in engineering design, anytime you finish your design, in virtually every design, there's always the issue of safety, factor of safety. So, but in this case, we have two safety factors. One is for infiltration, one is for flow. Now, when we're doing water reticulation, like Abuja, let me give an instance for the case of Abuja. I've seen people say that the water demand per person per day for design of Abuja is 230. And when I hear it, I laugh. Because when they designed Abuja in the early 80s, even Germany, or in Germany, they did the design, they were using 150 then. So what they used was 100, but they multiplied by a factor of safety of 2.3, which is about the maximum based on 1 million population equivalent. So many people who are oblivious will tell you that Abuja 230. It is not possible. The only country that uses very high water demand is like the United States, because they are very wasteful. They waste a lot of water. but based on European design and many other country design. In fact, Federal Ministry of Water Resources now, for their rural areas, they are using 50 liters per capita per day. So these two sets of factors shouldn't be a confusion. It is a statutory standard that you must incorporate. When it rains, no matter how you protect your sewer line, there will be infiltration water coming inside. So in your design, you must factor it in. Then for the fluctuation in your flow, which could be caused by anything, you also multiply by a safety factor. For the training next week, that is where this factor of safety will be more pronounced. Why it is not too pronounced or it's become difficult for us, for some of us, is because the value we are using for the sewer is just the value for the intake, for the water, potable water intake, drinking water intake. So the assumption in sewer design is that garbage in is garbage out. So what you take, what you receive from water board, in quotes, is what you give to AEPB. So AEPB is not interested in how, they're not interested in collecting data. That's why you don't see meter in sewer line. Nobody meters you in sewer line. The input, what guides them to know what to bill you is what water board is giving you. And I told us something yesterday. I said in Germany, the cubic meter of water in Germany is 2.25 euro, 2.5 euro. Well, when they are charging you, they'll charge you 5 euro per cubic meter, because they're assuming that 2.5 will go to treatment, to waste. So the assumption is that if I give you 1,000 liters of water in a day, I expect you to discharge 1,000 liters for me. So that's how it came about. So, okay. Please, any other question? Somebody is asking question. Please show us all the training video at the end. Yeah, I will share this training video. Don't worry, you'll get it. The video for yesterday should be ready by now. I think I'll share it. I will normally put it in the YouTube. And the video for previous trainings are already on YouTube. So anybody that have gone to YouTube would have got to see it. But just type this topic, the exact word of this training. You will see the videos on YouTube. Oh, okay. So this is where we are. I'm explaining how we got about that table, how that table came about. How that table, because when I put in this table now, if somebody doesn't explain this table for you, it's almost impossible that you understand it. So how do we come about this table? Number one, this is our A, catchment A, pipe A. The area is 163. Therefore, the Q, the flow in liter per seconds, is now the catchment area multiplied by the flow per hectare. The flow per hectare, which you have done, if you multiply the two, you get 6.26. When you come to catchment B has an area of 5.47. The same flow, the same unit flow, because the same consumption is the same wastewater flow that everybody produces, irrespective of size, is now 2.19. But because catchment B is downstream of catchment A, therefore the cumulative flow for catchment B becomes the flow for catchment A plus the flow of catchment B. And that will give us 8.46. When you come to catchment catchment C does not have any upstream. Therefore, the cumulative flow for catchment C remains 5.64, which the cumulative is also 5.64. So here it says finish the column 4 to 6. That means the other ones were expected to finish for these other ones. So when you come to catchment D, this is the flow. Or let me call it the static flow or the base flow. But the cumulative flow now will now be, remember where catchment B is. Catchment D is. It will now be flow coming from A plus flow for B plus flow for C will give you the flow for D. And that's exactly what we have here. Flow for D will now be A plus B plus C plus itself because himself too is contributing sanitary flow, and that will give you 15.66. When you go to E, E does not have any dependence. Let me use that word. It does not have any upstream catchment. Therefore, E remains E. E remains E. It's independent. But when you come to F, it will change. F is now, what do you have for F? F will now be the value for D plus the value for E. Can somebody confirm that from the chart? Instead of going through A, B, C, D again, no need for that because D already has captured those upstream. So the value for F will now be the value for D plus the value for E. Any question about that? The value for F will now be the value of D plus the value of E. I'll give you the value of F.
I think all this part is very clear.
It's clear?
Mm.
Oh, that's wonderful. Okay. Okay. Do I have any confirmation of that? Can somebody confirm via chat or verbally that we understand how this table for sewer is computed and why, as we're moving towards the treatment plant, the value inside are increasing? Okay. Then the next thing now is we come to storm. We come to storm. Storm. Remember this training about sewer and storm. Yes, I understand. Okay, Engineer Kewe. Okay, that's good. Another person? Bila Baba Mohammed. Do you understand it? Ibrahim. You guys grab it. And who again? Engineer Anthony. Did you understand this part? How we came about this sealer computation? Do you understand this part? Because this is what we're looking for. Column column 6. I can hear you. Talk to me.
I don't understand it clearly. I've been struggling with the internet.
Okay.
But now it's clear.
Okay, good. Thank you. So now, with this now, we'll go to upside. We either go to sizing.
Sorry, sir. I said
yes?
My internet is okay now, not that I understand it clearly.
Okay.
I've been struggling with the internet, so
you get the video
of your training.
You get the video. You get the video.
Okay. So what we did here now, let me quickly do it in 1 minute now. Let me explain it through this video, through this.
Yes.
The wastewater flow coming from A will empty itself into B.
Yes.
When they get to D, the one from C will join them.
Yes.
When they get to F, the one from E will also join them.
Yes.
So at point A, the wastewater flow will be the unit flow multiplied by the area.
Yes.
When you get to B, the value in B will now be A plus B, will give you the total discharge at B.
Okay.
Total discharge at C is the discharge at C, which is the area multiplied by the unit flow of wastewater. And the unit flow of wastewater is the unit water consumption multiplied by the safety factor, multiplied by the number of people or the population density of that place. That will now give you the unit area. So when it comes to D now, the wastewater flow in D will be the wastewater coming from A plus the one coming from B, which adds up to the one from B, which the one from C adds, then plot itself. So for D now, if you go to the table, you'll be seeing that D is about 15.66. But
yes.
itself, its own self-contribution, its own specific base demand, base flow is 1.57. But because it is downstream of ABC, it is now A plus B plus C plus itself will now give you 15.66.
Okay.
But when you get to number E is just on its own. It does not have anybody upstream. Therefore, E remains E. So this is E and this is it. But when you get to F now, F will now be the value for D, which is this 15.66 plus the value for E. I don't need to start counting A, B, C because D have already incorporated A, B, C and itself.
Yes.
Thank you. Why this is important is that is why as the pipe size is going towards the treatment plant, it's increasing in size.
Okay.
That is what the mistake a lot of designers do. When they do their design, they use a uniform pipe size. It's wrong. It's not possible. As it's going towards the consumer or it's going out of the consumer, it's either increasing or it's decreasing. So at this point now, what you now do is once you've gotten this cumulative, you now go to sizing. You go to do your what we call pipe sizing. So let's do the pipe sizing for sewer. So to do your pipe sizing, you use charts. There are many charts online. I gave us an assignment to download templates. I don't know how many people that did it, but then I will ask that at the end of the class. So you go to charts. There's a folder called charts. When you go to chart, I've included four charts for us. The nomogram are used for pipe sizes that are less than 1.2 meters. Then if it is more than 1.2 meter, I will recommend you look for charts online. But I've downloaded one, Federal Highway from US. I have downloaded one of their charts, which we use for storm, because it is only storm drain that are above 1.5. But any chart that is below 1.2 meters, you can use any of these charts called nomogram. The Candy Brook chart. Now, I included three. These three are dependent on the roughness factor. The roughness factor of the pipe will determine which of them you choose. Now, let's assume we are using PVC pipe. Let's assume we are using PVC pipe. So PVC pipe have low roughness coefficients. PVC pipes have low roughness coefficient. And what do I mean by that? I'll prove to you now. If I go online now, for instance, just stay with me. If I go to Google now, I type in Google, and
we can't hear your voice again. Oh. We can't hear your voice. Oh.
Okay, sorry, I think I muted it mistakenly. So now, if you go online, you will see. Okay, let me choose the images. Now, these are roughness factors. If you look at my chart, there are hundreds and millions of them. Okay. So you could see cast iron, for instance. If you are using Hesing-Williams factor, if you're using Hesing-Williams formula, cast iron is between 130 to 140. If you are using Weishbach, it is cast iron is from 0.85. Then concrete is between 1 and 10. Why is it between 1 and 10? Why are they in the range? Because some concrete are very smooth, some are very rough. So it depends on the roughness. If you're using galvanized iron, it is about 0.5. That one is fixed because galvanized iron is always fixed. It's a universal thing. That one can be fixed. Then if you are using plastic pipes, you can see that the roughness factor is around 0.05. okay, and so on and so forth. So why I brought up this is to let you know that determine the roughness factor of your material is not rocket science, it's not a big deal. Okay, you can just go online and you determine it. But for the purpose of this class, I've included for 3 of them. 0.1 is for PVC. You can write it down if you want. 0.1 millimeter is for PVC because PVC are very smooth, they are less rough. Then no more ductile iron are 0.4. Then concrete pipes are from 1. So the question is, which one do we use? So let's assume that we are using PVC pipe. Therefore, we're going to use the monogram for 0.1. So this is what the chart looks like. And that is the chart used for your pipe sizing. Now, for every design you do, whether you're doing storm or you are doing sewer, is either you use a chart or use a table. Unfortunately, I don't use table, I use charts. But there are some code and standards that have provided table. So when you get your value, you read the table. So let me show us how to read this table. This table is very important. So if you go to the title block here, you see that this table is for PVC pipe, and the frictional losses or the roughness factor is 0.1. And this chart is called Kaman Brandil Colebrook. There are many of them online. I've used different ones and they're all the same. So on the horizontal, on the x-axis, it is the discharge in liters per second. Everything here is liters per second. The only difference is that as you're getting here, it changes to 100, 200 liters per second, 300. Then once you get to 1,000 liters, it changes to unit variable, but they're all the same. So here is liters per second, here is meter cube per second. But all of us know that liter per second and meter cube per second is just a factor of 1,000. 1,000 liters make 1 cubic meter. I say it again. 1,000 liters make 1 cubic meter. So when I'm saying liter per second, I'm saying cubic meter per second, is just the same thing. It's just a question of how many zeros multiplied by 10 raised to the power minus 3 or divide by 10 raised to the power minus 3. Okay. Then on the vertical, you have the slope. You know, I've been talking about slope. I've told us before that slope is a very important factor in pipe sizing. So the vertical is in slope. The horizontal is in discharge, is the discharge. And the third factor, remember I said there are 3 things you need to size any pipe. The flow or the discharge, the slope, and then the roughness of the material, which is a function of the material. But in this case, we don't need roughness because this chart is meant for a roughness of 0.1. So the roughness is already fixed. So we have fixed that's a fixed boundary, the fixed boundary condition. So the next thing now is you get your slope, you get your discharge, and you can size that pipe. Now, where you don't have a slope, you make assumption, you make reasonable assumption. But now, ideally, you expect it to have a slope so that you can do a very accurate, detailed design. And remember again, once the slope is more than 4%, you don't exceed 4%. So if the slope is more than 4%, you use the value for 4%. Let me say it again. When the slope is too high, 6%, 7%, use the value for 4%. So 4% is the maximum fixed upper boundary. 4% is the maximum fixed upper boundary. So even if you see a slope that's more than 4%, the code says use the value for 4%. 4% itself is already enough. So it's enough steeping. In particular is that? We're using German code, DVR. So but if you go to DVR 118, I have been mentioning it here.
No Nigerian code for it. But, so there's no Nigerian code for it. Okay.
Hello.
Yes.
Hello.
I can hear you, sir.
Yeah. Yes. I know you have been quoting the German code, but is there any overlap? The Nigerian code, like when you were discussing about the population data, I know that for Nigeria is a few years ago, some 5 years ago, it was 125 liter per capita per day.
Okay,
I know that just recently, I think last year or so, it was changed to 140.
Okay.
No, that's linking with the Indian standards. Is there any overlap? Can we, in this, make reference to German codes when we have our Nigerian standards, or do they overlap?
Yeah,
I'm not familiar with German codes.
They do. Pardon me, sir. I think it's that's why when we started this class, I said part of what we're going to learn here is also a different perspective. This code and standard thing, there's no big deal in it, sir. The German code have transformed into Euro code, and the British code have merged with Euro code.
Yes. Okay. Yes.
And we are using British code, so it's just the same thing, sir. The only difference is that, like yesterday, we talked about if you are laying a pipe during in snow ravaged area, you make sure it's about 2 meters deep. In Nigeria, you don't need it again because you don't have snow. Now, for the water.
Yeah, because even when you were.
Go ahead.
Hello, sir.
I hear you, sir.
Because even when you were making use of the rational formula,
yes,
for Nigeria, the Nigerian standard, if you are using SI unit, you introduce 0.278.
Okay, good.
But I realize that we don't. Hello.
I can hear you, sir. Can hear you, sir.
Yes. So we introduce when we invoke SI unit, we introduce 0.278 CIA.
Okay. Oh. 0.28. That's a conversion factor, sir.
No. Yes, that's 0.278. It is the SI unit.
Yeah, it's a conversion factor. Yes, you are right.
Yes.
It's a conversion factor. To convert millimeter per hour is a conversion factor. It's not a good thing. I know what you're talking about, sir.
No, I know. I know, but that's what I'm saying. I'm not saying it's a good thing. I'm saying that because of where you are taking your reference from.
Okay.
So
now,
those are the variations we need to.
This is this discussion I always love us to have. Okay, it's very important. As I said, I'm not trying to belittle codes and standards. Somebody once abused me that Nigeria is a codeless country, but that's a story for another day. Now, I've gone through many codes. I know that British code. Let me tell you something that happened in Europe on the funny side. If German says our steel is 460, the French will say our own is 460.5. That's their rival. The British will say, no, we are British. Our own will be 460.8. So the difference is very minimal. Like I know during the early days of NSC, we wanted to adapt German code. Germans have adapted their code to Iran, DVR. They have adapted to Malaysia. I know of those. And they have adapted to South Africa. I know of these 3 countries. This is what our NSC was supposed to do. But thank goodness that they did the one they did for the storm. We don't have those issues. For Federal when he was Minister of Works.
Then they even done for concrete also.
Recently, as at 2 years.
Yeah.
So I think we're getting there. But let me shock you, sir. If you bring that code and bring British code, you find virtually no difference. True or false?
You're right.
Why? Because it's not like it's a bad thing or illegal thing. No. Codes are adopted and adapted. If my environment and your environment are the same, why should I crack my head going to develop, invent the wheel? Are you with me?
Yes, I am.
Unless I'm your rival, maybe Nigeria and Ghana, now, if it's Ghanaian, we don't want Ghanaian thing, we want our own thing. Okay. Just pick it up and just upscale it. So as I keep mentioning German code, forgive me, but I mean, that is what I know how to do. It's
okay. It's allowed. I just wanted to. I was just.
It's a good discussion. No. It's a good discussion. I love this discussion to come up. A South African once abused me and said that Nigeria is a codeless country. Real life. And that is one indictment on NSC. For the past 20 years, we've been doing code and standard. We've not gotten up to, we've not developed one. One. Every president will come and say, code and standard committee. Just come up with, just find one country that has a similar code. Remove their name. I know when we paid a courtesy visit to the Korean president, Korean registrar. You know what he said? Quote me. I'll tell you that's what he said. He told Nigerian engineer, he said, you guys should go and look for any code, bring it, tear the cover, and put Nigeria on top. I will stamp it and approve it. I'm quoting my name is Engineer Uche. Go and tell Rabiu. That's what I said. That's what he said. But yet we are here to do that.
It's okay.
And if you tell them, let's start, forget it. So let's continue, sir.
Okay.
Let's just find any code. And you appear to be using Indian code.
Wait, we will not continue. Now, the senior colleague just mentioned something about using 0.278 of CIA in Q or something. What are you converting from? What? From
thank you. I'll show you now. You are converting millimeter per hour to meter cube per second.
What did you say?
You are converting millimeter per hour to meter cube per second. Let me show you where I use this. Let me show you what it means. Sorry, are you seeing my screen?
Yes.
Okay. Well, let me just see. Look at it. Look at what he meant. Are you seeing that 0.28 on my address bar? Now look at this now. This is 140.
Yes.
This is one. Look at my address bar. Look at my address bar. This is my address bar. So this is, this is 140 millimeter per hour. Is the rain intensity. And now I want to convert it to meter cube per second, which is SI units. So what I did was to multiply 0.0028 multiply by the hectare, multiply by the rain intensity, then multiply by my coefficient. So all this multiply, all what we're interested is to say 0.028 multiply by E34. But because these two are associative, as we say in mathematics, they are just there. This is a very good question. Did you understand this?
I'm still looking at it.
Everybody in the class. Now, if millimeter per hour is not meter cube per second, so for me to convert it to meter cube per second, I'll multiply. It's not like, okay, you know what? It's a funny thing. You know, last week I did a training in Niger State for the Ministry of Works. I told them that if you're doing your design, just have Google by your side and watch this now. Watch. Convert millimeter. Watch it now. Millimeter per hour. Sorry. Millimeter per hour. So look at it. It has given me many options. So if I just click this now, that figure will pop up. Look at the figure, it has pop up. Look at it somewhere here. Look at somebody say, help, please help me. It's a conversion. If you sit down now, if you convert millimeter to meter cube, you convert hour to seconds. Okay, let me even do it. Why am I even shouting? Maybe something I can do. Okay, now watch me. Let me go to my whiteboard. Let me clean some things now. We want to convert millimeter per hour to meter cube per seconds. Millimeter to meter. You divide by what? You divide by 1,000.
By 1,000.
But we're talking about raised to power 3. Am I right?
Mm-hmm.
So it will be raised to power minus 3. I don't know how to put this. The zoom is limited, but this will be raised to power minus 3 into 3 places. I won't do much about this. We're all engineers, we can do this. Then hour, want to convert hour to seconds. It is 3600. So 3600 divided by 10 to power 6. Then hectare 2 will be multiplied. 1 hectare is 10,000. 10,000. So it's going to look at something like this. This is 3, 3, 3. Thank you. So do this mathematics. If I do this mathematics, you get something like that. So this is 4. This is 4. So let me eliminate 4 pieces. 4 is gone.
How did hectare come into millimeter
Yeah,
per
because
hour, meter cube per second?
because it's per hectare. So just hold on. You see this formula, gentlemen, eh? That is where the 0.28 came about. By converting this to convert meter per hour into meter cube per second. For you to get meter cube per second, it means this is a linear, millimeter is a linear, so you must multiply by area. So if you just want to save your time, just go online and said converting formula per hour to runoff. So you see a lot of formulas coming up. So this one says
I think we should move on. I think we are concerned with this point now. Maybe we should move on.
Okay.
I think we can continue.
Okay, let's continue. But is a conversion factor? Is a conversion factor we can do? So now, back to the table. Is there any question on this table on how we got this? So with this now, we go to our table, to our chart.
Can you see anything on your screen?
Okay. We go to our table now. Now that we have gotten our discharge, not just the individual discharge, but the cumulative discharge at every section of the pipe. So for pipe A now, we have the slope. The slope is 1 in 200. The slope is 1 in 200. So 1 in 200, you go to your chart now. 1 in 200 should be whatever the slope is. Let's assume the slope is 1%. Let me make an assumption. You can really get this little slope. So if the slope now is 1%, for instance, which we have converted to per mil, you now read off 6.25. 6.25, somewhere here. You now read it until you get to the slope. If you get to this the slope, it will fall in between. Okay, for the first slope, I think we have we have 1 in 200. Let me use that one as reference. So 1 in 200 means 1 divide 200. Then multiply by 10. That is 0.05. Okay, so 0.05 is 5% if you convert to percent, because the slope is calibrated in percentage. The slope is calibrated in percentage. So what we now do is under 6, the discharge is 6.25, which is between 6 and 7. You read it against 5%. It will fall in between, is somewhere here. So it's falling between 100 and 125 diameter. I will encourage us to open our monogram chart for 0.1. So it will fall between 100 and 125. So what this means is that you choose the biggest of the two. You choose the biggest of the two. So if it falls in between this chart, the diagonal is the pipe size. And the diagonal moving from left to right is the pipe sizes. And the diagonal moving from same left to right, but downwards, is the velocity. So what this chart does for you is that you give it 2 parameters, it will give you out 2 parameters. The 2 input parameters you need for this chart are the slope and the flow. And the output of the chart will be your pipe size and the velocity at that point. Why is the velocity important? The velocity is important because yesterday we talked about minimum required velocity in a C1 network, the minimum and the maximum. So if you design your pipe and the minimum and the maximums are not met, then you need to work on, you need to do so, you need to work further on it. So for the first A.
Sorry, can I ask a question, please? The folder that has nomograms, that's for 0.1, for 1, and for 0.4. Which one are you using?
We're using 0.1. I said it that we're using PVC pipe.
Okay.
We're using PVC pipe, and I went online and I Google and checked the pipe size. Assuming you forgot, but I've said it now. Assuming you forgot, just go to Google and said PVC pipe of different pipes. It will pop up. So 0.1 is the least, is the one for PVC pipes. 0.4 is for ductile iron. And anything from 1 and above is for concrete. And it depends on the roughness of the concrete. Some can go as high as 2, 3, 4, the roughness factor. But you know, in engineering design, you design based on worst case scenario. So what 1 can do, 3 can do it also. So that's the meaning. So that's why most things in this design we're doing is the ranges. So you use the worst case just to know the one that will capture the worst case. So there are some PVC pipes, especially this new one from Turkey. Their roughness is very, very low because of this, their smoothness. The losses are virtually 0. But then you still assume a minimum, which is 0.1. Okay, so if you now go to the discharge x-axis, this is 6. You go against 5%. Well, we got 5% now. Slope is a dimensionless thing. It's a dimensionless value. But our chart is calibrated in per mil. Oh, per mil.
Hello, sir.
Per mil is per 1,000. Yes? Ask me, sir.
The 1 to 200%, 1 to 200 slope is 0.5% slope, not 5% slope.
Now, this chart, if you look at, thank you, that's a very good question. That was what I was trying to say. This chart is calibrated in per 1,000. Yeah? Now, per 1,000 means, you know, there are different units of calibration. Percentage is per 100. So if you look at this symbol says 0/00. So this is per mil. So whatever value you get, you multiply by 10 to be able to use this chart. If you remember in our school days, most charts we use have some precondition, what I call preconditions. So for you to use this chart, you have to convert your unit into per 1,000. So if you want to convert it straight into per 1,000, you just multiply what you got by 1,000. So what did you get, sir?
I get 0.5% slope.
No, what's the value you got? 1/200 gave you what?
1/200.
Multiply by 1,000.
1/200, that is 0.005.
multiply by 1,000.
It's 5. Okay, so 1 to is 1 to 1,000.
That 5, you don't say 5%, you say 5 per mil.
Okay.
It means 5 per thousand. You know when you say 5%, what you're
5 per
actually saying
thousand.
is, yeah, God bless you. When you say 5%, what you're actually saying is 5 over 100.
Mm-hmm.
But when you now say 5 per thousand, when you say 5 per hectare, it also means 5 over 10,000. These are units, these are different units of measurements.
Okay.
So for this particular chart, it is calibrated in per thousand and it is indicated here. Yeah,
okay,
look at this symbol. This symbol is 0 over 0, 0. Percent is 0 over 0.
Okay, clear.
And it's a very important thing to explain about this chart. And those are the only explanation I have to give. The other explanation is that this chart is exclusively for a fractional factor of 0.1 or less.
Okay, thank you.
Thank you. So thank you very much. So now what did you get? Can you read what pipe size can take that sewer? So the pipe size will now be, let me use my annotation. So stay with me.
250 should take care.
No, sir.
Because it's still within the cleansing velocity.
No, it's not. It's not. Can't be 250, sir. I got 125.
What do you get?
125.
At 125, 5% slope. That is the flow is about 7 liters per second.
Yeah, between 6 and 7. I mean, you can't see 6.25. So why not just assume 7?
Okay, already have the flow. So okay, already have the flow.
We have the flow already.
Okay. Correct.
Good.
Please, I'm not following that point.
Can you look at the horizontals and you see where the discharge we got was 6.25.
Okay.
And the slope at that section is 5 per mil. That is 0.5%, which is 5 in our chart. So you now draw a line from that 6 point, draw a line. This is 5%. I draw a line.
Where's the line now? Is it horizontal? Okay.
Horizontal.
You draw a vertical and horizontal line.
Horizontal. The way we read charts, sir.
Yeah, okay. I'm seeing now.
The usual way we read our charts.
Yeah, this the normal way. Okay. Okay.
Sorry, I'm battling with my system.
The challenge I'm having is because I'm not using my system.
Okay.
And so I'm using phone. So that's the problem I'm having.
Okay. Now look at it.
I can't play around.
Okay, now watch your screen. I agree with you. So look at it now. This is 6.25. I'll draw a line up.
Yes.
What did I get?
Okay.
That's 125. So the pipe size at that point is 125 mm. Now, because it's falling between 100 and 125. And there's something I always tell people in infrastructure design, it's better to over design than to under design. Any disagreement? It's better to over design than to under design. But then there should be a limit to it. Good.
Design
so now
for the worst condition.
Worst conditions are. So now, we are using 125. So that's the pipe size to provide.
Okay.
Then we go to the next one. The next one is 8.
It's understood.
Thank you. The next one is 8 point what?
Hello, sir.
Yes, I can hear you, sir.
Yeah, please, can you just for explanation, the velocity, how do we interpret the velocity for those cars that's not clear with?
Thank you. So now that I've gotten to this point, please feel free to ask questions. That's why you're here. This is the point. So I will now go this way. So the velocity is 0.6. It's falling between 0.6 and 0.7. Which one is the worst?
0.7.
No, sir. The worst is 0.6. You know why it's 0.6? Because I'm working against 0.3. So which one is closer to 0.3?
Okay.
So one other thing from this chart.
Hello, sir. Even in British standard, the self-cleansing velocity is about 0.7.
You say safe, not the minimum.
That's the minimum. We check some BF standard. They said the self-cleansing velocity is 0.7. Some
Check
say
again.
0.6.
Check again,
Yeah.
sir. It's 0.3, sir. I'm 100%
sure. The range is 0.3 to 3.0.
It's not that. It's 0.2%. 0.2%.
So me, I'm saying 0.3. It's still, sir.
Yeah, it depends on the code they are referencing. So
no, sir. No, we are saying the same thing. You say safe. You know, in engineering, there is minimum, there is maximum, and there is safe.
And yes, we're talking about standards.
Optimal. This is optimization. No, it's not the same thing. No, it's the same. It says safe. It means you should aim for safety, but the worst case scenario is 0.3. And the worst case scenario on the upper side is 3. Some standards say 5. And that brings about the issue of code and standard. That's why code are important. But then you can see that all of us are almost saying the same thing to an extent. If not for want of time, if we finish, I'll Google it and I'll prove it through Google.
The guy is that 0.6 is the settling to avoid the settling velocity. So that is the 0.6 to avoid settling situation inside the pipe. So you make it 0.6. It doesn't mean it's the minimum.
So we are saying the same thing. You are saying the same thing. Okay. So whether British standard or Euro standard, they speak. As I said, I've been in, me and Sunday we've been in Germany. If German says our own is 0.15, French will say our own is 0.14. I know that one. Just to bring in a French coloration to it. And at the end of the day, whether you use French or German, you land at the safest design, because nobody will go below that, because whether the pipe is located in Europe or located in Nigeria, if this slope is less than 0.3, the tissue paper will be stuck there. I mean, if I take it, unless you take it to the space. Okay, let's continue. So the second one, I'm happy everybody's following. Please, if peradventure you're not following and you're not asking questions, well, I wouldn't know. So the more you ask, and these questions they are asking are very intelligent questions, and I'm impressed by the caliber of people we have in the house. I think we are showing that we already know some of these things. But as I said, I'm not here to teach you what you don't know, but I'm here to show you a different perspective, and that is one thing that's lacking in our discourse. Trying to understand other people's perspective, not that they are doing the better thing or they know more than you know, but that perspective will help you to shape what you know, to help you to readjust, and then maybe to improve on what you already know. And that's what the training is all about, to improve on what we know all these things already, but then to improve on our knowledge and to be able to have a common, to arrive at a common platform. I told us about a big consultant in Asaba who came into Abuja. Why? Because we just wanted to be sure of what he's doing. And when he came, he said, yes, that's the same thing I've been doing. He went back, and that's it. Okay, so the second one now is to do the next one. The next one is, what's the value again? 8.46. 8.46, that's for B. So what is 8.46? Let me just prove to you that the pipe sizing will be increasing as we're going downstream. So this is 8.46. So let me just assume 9. Sorry. So 8.46 on the horizontal. .46 is somewhere here. Then I don't know what the slope is. But let's assume that the slope is the same. Huh? If the slope is not the same, then the new value will be somewhere here. And that will be what? 150 mm pipe, because this is the biggest one. This is the biggest one. This is the one I'll use. Huh? This is 150. Is that understood? Any question?
No, it's okay.
So the second one with 150 pipe. So I'll go to my column. I'll go to my column and I indicate 150 mm pipe. And mind you, this is for circular pipe because it has to be a closed pipe. Are we together?
Yes.
Good. Now we'll go to the next one. And
then the velocity. The
velocity. I'll read off the velocity. The velocity has improved. Yeah. The velocity. Oh, the velocity is 0.6 smaller. So the velocity is the same. 0.65 or whatever. Or use 0.6. 0.6 still on 0.6. Okay. If you go to the chart, you find out that maybe the velocity of catchment A and B.
Sorry, sir. Sorry,
yes.
Sir. I hope this chart accommodates the fact that we are assuming that the flow is partly full.
That's a very good question.
Is it flowing full or partly full?
We've not factored it in. Actually, what we factor that in is in the storm. But that's a good question you asked me. By the time we arrive, I remember we've already used safety factor of 2 and infiltration factor. So if you have used those factors very well, if for the sewer,
they capture this.
He captured it. Thank you.
Okay.
But for the storm, we implement it, we divide by 0.9 before we got to this value. But you as an engineer, on your own, like that's what I do. Like in my design I did, when I got everything, I divided by 0.9. You know, divided by 0.1 means I'm improving it by 10%.
Okay.
And the client saw it and he agreed, it's okay, no problem. So I increased my safety limit by another 10% on my own without recourse to any code.
Okay.
Yes. That will be if I'm not sure of the safety factors I've used, or if I'm not sure about some input variables, which is what we often do when we do our estimation.
Because for this, if it's let's assume it's an open drain, you can think of maybe anything you can add.
Look at where we added it. Here, you see this column number 16.5. When we got the wet water flow, this is the wet water flow. It gave us 738.41 as a storm flow.
Yes.
We now divided it by 0.9 to now get 820. It is this 820 that we used against our chart, and we got 800 mm diameter.
No, it's okay. It's okay. I understand.
That's a good one. That's a good question. So now we are moving over to catchment C. I don't need to do for catchment C. You know why? I have done for catchment A 6.26, and catchment C is 5.68. Will I be lazy if I assume 1.25?
No.
Good.
No,
we are engineers. We all do these things.
You're just saving time.
Thank you. Then let's go to catchment D. Catchment D is 15.66. I will now go to my chart and go to 15.66. This is 20. This is 15. 15.60. So let me use it. Let me assume this one. So I'll draw my line. Sorry. Now let's take it slow and steady. This is the main point of this training. And if you can grab this, forget the other thing, because for the software, it is garbage in, garbage out. If you get this wrong, then you give him the wrong input variable. So for the...
Maybe you can click out to remove the highlights. Okay.
Okay. I don't know how to use that one. Okay. So this is 15.6. So 15.6 is close to 15. I don't know the slope, but someone can confirm the slope from the table. But let me assume the same slope. If I'm to assume the same slope here. So that will be how many? What pipe now?
2.
100, which is 8 inches pipe.
That's 200.
Okay. Did I tell us that in sewer design, based on the standard we're using, that they said that the minimum pipe size is 150 mm? Did I mention that yesterday? I think I did.
Yes, you did.
So in all the design I'm doing,
and the maximum is 900.
Value, no, there's no maximum. But for PVC pipe, there is a maximum size pipe that PVC cannot take. So that's the one that's limiting it. Not based on the code and standard, but based on availability of material and based on the depth of laying. Did you get that point, sir?
Yes, please.
Some PVC pipes will tell you, if not for in the last 5 years, you can't see a PVC pipe that is more than 600. But based on technological improvement now, you can get a PVC pipe of 1.2 meters in the market. So the upper limitation is limited by material, not by the code and standard. But the code and standard says 150 mm. So if any day you see anybody laying sewer line in an estate, in a district, and he's using any pipe that is less than 150 mm, he's doing the wrong thing. Even if you get that 4 inches pipe can take it, the code says provide 150. So 150 becomes the minimum acceptable standard. And it makes sense. Let me tell you how they came about that. Because sometimes sewer carries, they carry things. You need to go to the treatment plant sometimes and you see the funny thing people throw into the sewer. So many things that you can't think of. They flush a lot of things down the toilet. So that 150 also provide for tissues and some suspended solid materials that might escape through the system and get into the pipes network. And you know, if anything gets there, clogging and blocking, not even outright blockage. And when these blockages happen, it's always disaster. Okay, so you can see. So let's go to the last one. And the last one should be F. So the last one is pipe F. Pipe F is what? 23.49.
23.
That's a huge flow. 23 is a huge flow. It's a very huge flow. So 23.49. You can't do. Sorry. I'm sorry. So 23.49 is as good as 25. So I go up to here. Sorry, yeah. It's still 200, it's 250. Hold on. The 3.49 should be somewhere here on the same slope. Okay, it would just take 200, same 200.
Yes.
Same 200, yes. So any questions so far? Before we go to stormwater, I want to give 3 minutes for questions. If you don't ask questions, it's assumed that you've understood everything. Just 2 minutes, sorry. We are done with sewer design.
But you, for the last piping, you still choose 200.
Yes.
There is, I think by that, if we have traced correctly, there's a, okay, well.
You know, my aim is for you to know how to trace it. The values are inconsequential for me. Because I can see there are some mistakes, like my screen shifted. It didn't reach 5% again, but the concept is for people to understand how to read the charts.
It's okay.
And you know the funny thing, for the storm, there's this chart I used because some of the storms we are bigger than 1.2. So I used this chart in the US chart from US Federal Highway Manual, and the chart was calibrated in inches. So what I did was to do conversion. So most charts in the market, you have to understand how to, any chart has its uniqueness. You can't just pick up a chart and start using it. You need to read it and know how to use it. It's always a standard. There must be an accompanying test on how to use that particular chart. So for this, my chart that we use, this is a chart I was taught with, that was used in teaching me. The number one thing you do is to note that it is calibrated in per mil. So whatever unitless value you got, multiply by 1,000. Then to also understand that 2 input variables will give you 2 output. Will give you 2 output variables. And then if you look at the horizontal, it's a bit funny. It started with meter per seconds and it jumped into meter cube per seconds. But then I told us that meter per seconds and meter cube per seconds are technically the same thing. It's just a difference of 1,000.
Just 1,000.
1,000. So you can see that when they got to this, when they got to 70, they went to 100. From 100, they went to 200. And then when they got to 1,000, it became 2 cubic meter. So I think at the end of the class, just scan through the material, through the chart, and just get mastery of it. Okay, so let's go to stormwater. We have 1 hour to deal with that. But I know that the foundation I believe. Now for stormwater, the same thing applies. The difference now that you're not dealing with more of what do I call it? Let me mute.
So the outputs of this chart now is the diameter for pipe and the velocity.
Hello. Hello, you say something? Yeah. Say.
The input for this chart is the slope and the flow.
Slope and the roughness.
The roughness.
Mm-hmm.
Is the slope and the flow now.
Look at the 3 things to size any pipe anywhere in the world. Any kind, even gas piping.
This particular chart.
Okay, then you have fixed the roughness. Yes, it's only 2: the slope and the discharge. The flow and the discharge. The slope is on the vertical and the discharge is on the horizontal. Why the roughness is fixed. Are we together? Like I lost him. Hello?
Hello, sir.
Yes.
Now, some charts normally post. I don't know whether this chart also accommodates that. Post like if you mentioned, I've seen you post. There's a white badge. It has William, the frictional losses. So when we use these charts, they have been accommodated. I want to believe they are inbuilt. So you no longer go to quantify those ones, Abi?
Yeah, this chart uses that Weisbach. You know, that the Weisbach is for SI units. I think I Googled it. I brought that thing. If it is Hesing-Williams, you'll be talking about 100, 130. The Hesing-Williams roughness factor for a PVC pipe is 130, between 130 and 150. Are you with me, sir?
Yes, so the frictional losses have been taken care of now.
Yes. What do you mean? I don't understand what you mean by that, sir.
Now, the head losses during flow. If you are like when you do water reticulation, at all the nodes,
in water reticulation, you fixed what formula you're using to determine the frictional factor, whether you're using Weisbach, Hesing-Williams, or Chasey-Manning.
For whatever kind of network, what I'm trying to explain is at each node, you have frictional losses now that are head losses, which you must account for in your the entire network.
Okay, I understand where you're going from now. They are more pronounced in the water reticulation. They are more pronounced in water reticulation, not seawater.
Okay.
Yes.
All right.
They are more, because in water integration, you are careful about losses. It's a major factor.
Yes.
Because you have your head. You have your head.
Because losses is even a variable, a factor that must be accommodated.
So yeah, you are careful about your head. You know your head. You have a head that you're trying to manage.
Okay.
But in this case,
I understand.
Okay, thank you. We can't hear you well, sir. Your network. I know it's a network thing. Hello. Okay, so let's move over to the Siwa now. So for Siwa we have, I need to clean it up. So for Siwa now, our focus now, remember our Siwa formula, CIA. So the area is there, A is there. So intensity now is what we're looking for now. So we have our intensity, we have our C, which is the runoff coefficient. Hello?
Yeah, discussing the storm drain. Yeah.
Oh, sorry.
Now.
But we're on storm now. Thank you, sir.
Yeah. Okay.
Thank you. We're on storm now. Thank you. So for the storm now, we will now move over to CIA, where C is the coefficient of runoff, which is the first chart here. Coefficient of runoff. Yesterday we discussed how we got them.
So now got it. Same Monday.
Then the rainfall intensity, we got it from our IDF. Rainfall intensity, I've included two materials where you get the rainfall intensity for all the states in Nigeria. Okay. So if your state or if your area is not there, why not do what we do in engineering? You use the worst case available. Okay. If you are designing for Kano, you didn't see Kano, you saw Castina, please use Castina or add something, depending on what the next one in Niger is giving you. Okay. So now, if you are doing for Guri, this you use the one for Lagos. Period. So this is the first column is the runoff coefficient. So if you multiply the catchment area by the runoff coefficient, you get the impervious area, which in my own customized templates, I called it effective area. I adapted that chart to my own chart. This is my own chart and nobody has it in Nigeria. It's me that have it. And I told us to go and look for our own online and modify it. So it's me that developed this one, but I leverage on what was produced and I decided to call it effective area. So this is the effective area contributing runoff. The original area here is 1.5 hectares. But because my runoff coefficient is 0.8, it means that my effective area contributing to runoff is 1.2, which is high, by the way. But that's what my boss then wants. The person I did the work for. That's what he wanted. Okay. We argued over it for a long time, and sometimes you just have to agree with people. Me, I know that 0.8 is high, but he was assuming that tomorrow the place will become like a ghetto, where everywhere is sealed up. Okay, and that means the runoff will be so high, like we're having in Lugbe and Lokogoma, in those in Abuja. Okay, where you see everywhere is being sealed up. Nobody's controlling anybody. Everybody's just doing a solid interlock everywhere without provision for greening. Okay, so if you now multiply the area by the coefficient of runoff, you now get the effective area. And that is what you got here in column 8. Column 7, multiply by, I hope you're seeing this here. So multiply the runoff coefficient by the catchment area, you end up with the area of impervious. For B, the area of impervious is this. For C, it is this. For D, it is this. I'm on column 8. Okay, if you multiply this by this, you get this. After now, you now do what we did in the case of the sewer. You now accumulate sum up. So for column A, the area, the impervious area is 5.8. But when you get to catchment B, because there is no outfall, there is no other exit in column in catchment A, it means that the whole drain, the whole runoff is coming into catchment B. Therefore, the effective area of catchment B becomes 5.8 plus 2.03. That gives you 7.8. When you come to catchment C is on its own, is on the outskirts. So catchment C remains catchment C. There are no upstream. But when you come to catchment D, it has two catchments that are emptying water into him. And those two catchments are catchment B and C. And then itself. Therefore, this catchment D will now be the value for the summation of catchment B plus catchment C plus itself will now give you the value for catchment D. Catchment E is on its own. Therefore, it remains same. But when we come to F, F will become D plus E. Knowing fully well that D have already captured the upstream catchments. Remember, we are doing this because we feel we are saying that the outfall is only one in that catchment. In other words, it's just like in Abuja. Okay, in Abuja, the stream coming from Wuse comes to the back of Ibro Hotel, comes to Uye, comes to Galadimawa, comes to Lugbe, from Lugbe is heading to Kuje. Understand me? So that's why you see some of this flooding that happening in Abuja now, happening in all this Lugbe area, because the catchment in town are coming to the Abuja River. So I'm just giving this description for, pardon those who are not in Abuja. I'm trying to say this to emphasize how we came about this increasing catchment. Let me go back to here.
I think that's the same way what we call that can works now. It's
exactly.
Not the same thing.
Exactly.
Yeah,
so this is always a tricky issue for a lot of people. That's why you see them having the same drain pipe, drain size all through, and it's very, very wrong. Okay, so if you now go to catchment F, you now see that catchment F now is the summation of catchment D plus E, and itself, it will give you F. So when you have arrived at this catchment, that means we have done with A and C. Remember, we're working with CIA. We have incorporated C and A to come up with A impervious. Hold on. Good. We have our major formula is arrow, the intensity times the area impervious. But the area impervious is the coefficient of runoff multiplied by the catchment. So now what is left is what? Is R. In the German code standard, they represent it as R. But in our own, it is I. Intensity, our own intensity is the value, the symbol is I. So the next thing we now do, before we now lift up our I, is to check, to do a check, to know if I'm to read off my I from the IDF, what value should I use? This is the IDF curve of Lagos, Ireland. So you can't just come in here and begin to pick values. Okay, there are two input parameters you need. Those input parameters are the duration and the frequency. The frequency is here, 1, 2, 5, 10, 25, 50, 100. So which one are you choosing? So you choose one. Then for the duration, you choose 10 minutes, 15 minutes. Or somebody will ask me, why should I choose 10 minutes? Why should I choose 15 minutes? And the answer is now what we're going to get in the next two columns. If you measure the travel time from A to end of A, it will give you 250 minutes. For instance, let me give you this idea. This is catchment A. If you go to the table, if you go to this table, the length of this catchment is what? 500 meters length. We assume a velocity. There's a process of computing velocity, but it's so ridiculous and it's so cumbersome. So what we assume a velocity of 2 meters per second. It's an assumption. And it's a safe velocity. The velocity of 2 meters per second is not too high, it's not too low. You can't choose something that's too low, meaning that the water will take a while to arrive at the end point. So if I choose a velocity of 2 meters per second, we know that the velocity formula is distance over time, maybe? Yeah, distance over time is velocity. Therefore, time becomes distance over velocity. So if the distance is 500 and the velocity is 2, it means that the travel time becomes 250 seconds. What do I mean by travel time? From here to here. That's the travel time. From here to here, 250 seconds. 250 seconds means 6 minutes, about 6 minutes. So it's less than 10. The standard says it. Remember, there's a place I told us based on some conditions, this is the value to use. So because it is less than 10, we now assume 10. So this column 10 is saying that 250 is less than 600. Therefore, assume column 11, which is 10. So all the places that you saw that the values are less than 10, we chose 10 minutes. But in the case of H, we chose 11.7 minutes. The reason is very simple.
Sir, can I ask a question?
Go ahead, sir.
Okay, based on your explanation,
yes.
If this is less than 250, we assume 10. Now, what we are assuming now to key in is what we call a time of concentration, yes, I suppose, which is affected by a lot of things. One of such is a slope, and yes, then sir, even the shape of the catchment.
Yes, sir.
Have we accommodated, are those ones all incorporated into these assumptions? Because we have realized that some catchment, if the slope is above a particular limit, the flow will be exaggerated, and so the time of concentration, will be shortened. I don't know whether we have, whether these are all built in.
Just look at my screen. Can you see my screen?
Yes.
Now, this brings about the issue of code and standard again. The German guideline, this is what it says.
Okay.
It says that if the slope is between
okay. So there's a standard. Okay. All right. I understand.
Okay. All right.
But you understand my question?
It's a perfect question, sir. It shows experience, and it means you're already in the system. I think you are here to gain another perspective.
Yes, I think.
I'm not perfect.
No. Perspective is also no, sir. Sometimes we travel abroad, not because it's just to go and see what they are doing and to come here and know that we are doing it right. Okay, so now this one that is above 10 minutes. This is how it came about 10 minutes. Let me just explain it. It came above 10 minutes because here, we always talk about worst case scenario. We're in H. This is H now. If you check the travel time, this is 500 meters. This is about 250 meters. This is about 250 meters. This is about 500 meters. That will give you 1.5 meters. So 1.5 meters. 1,500 meters. Divided by a velocity of 2. It will be giving you 750 seconds. So it's above 600. It's above 10 minutes, isn't it? So you now choose, that's why we now use 11 minutes here. And that is why rational method is, we say that rational method might not be good for areas that are more than 100 hectares. Because at some point, your travel time will be above 15 minutes. And those flow don't contribute to runoff. Those flow are more like inconsequential. Any flow that is not between 10 and 15 minutes is not expected to contribute to runoff. Is not flood capable. Let me use this is my own invented word. It's not flood capable. Okay. So when you come to catchment D, the time of flow is increasing, just like what our last speaker just said. That is why when we come to that point, we now chose 11.7. It is this value that you got here that you now use to know how to read your IDF. And that becomes your duration. All these things we are saying now is, how do you get your intensity based on the appropriate duration, based on the appropriate frequency? So for durations that are below 10, you can see that there are no values. Check in all of them. This is Lagos Island. This is volume 4 of Federal Drainage, Federal Highway Manual. I have shared it. It's in our folder. It's an open material. It's in the open domain. So if you check anything below, this is the number. This is the value for 10. So you can see from here that anything that is below 10, there's virtually no value for it. So that justifies what I just said, that it is between 10 and 15. So now, if we go back to our chart, ask yourself, what are we designing for? Are we designing for a rural area? Are we designing for urban area? We come to this. So let's assume we are designed for city center. Let's assume that this is designed for city center. So we're going to choose 5 years, a time period of 5 years. And to save us mathematical calculation, we choose a duration of 10 minutes. So therefore, and let's assume that this layout is in Lagos Island. So let's use the IDF of Lagos Island. So for 10 minutes, Lagos Island, we have about, for 5 years, we have about 160. One of our participants said they're using 150. Well, 150 are almost the same thing. So let's assume 160. In engineering design, whatever you assume, justify it. Just find a way and justify it. So if I to assume that now, it means I will now go back to my charts. When I get to my charts, I will now multiply, ignore from column 9 to column 11. They're just for time of travel time. So the value I get now, we got 160, but this place in Germany is almost like Nigeria. They got 126. So let's just assume they got 126. Okay, let's assume that one city is 126. So you now got 126 now. You now fill it here because the rain duration is the same. It's the same catchment. It's the same rain gauge. It cannot be draining differently from Ireland and differently from Ikoyi. It's the same. So that's why it's uniform, except where the time of flow time, where the duration changes to about 11. That was when the duration now reduced a little bit. But it didn't reduce much. At 12, at travel time of 12 or rain duration of 12, the intensity is still around 120, and that is in catchment H. By the time the rain goes to catchment H, that's come to 120 due to from the flow. So we now multiply. The next thing we now do is now to multiply the rain intensity multiply by the reduced catchment or the area impervious. Remember, we've been talking about CIA. So finally, we've gotten our I. Our I is on column 12. So I multiply by CA. Remember, this has become our CA. These are C, these are A. So A multiplied by C gave us CA, CA. Then multiply by I in column 12. You will now get your flow. So for catchment A, what size of pipe are we going to use? What size of conduit? That's the appropriate word. The conduit we're going to use is a conduit that will deliver, that will be able to carry 732 liters per second. So what do I do? I will now come to my chart again. I'll come to my chart, and this is where I now said, before I go to my chart, I will divide this value by 0.9 so that I'll know that it's partly full. The code says that to avoid surcharge in your pipe network, you should make sure that your flow is between 0.7 and 0.9. In other words, your carrying capacity of your pipe should be between 70% and 90%. Don't ever get to 100%. It does not mean it cannot be less than 70%, but the lesser it is, the more critique someone would do on your drawing, on your design. The more, will I say, bad designer you are. If you design a pipe and the maximum flow in that pipe is 40%, and all the time 60% is lying fallow, it doesn't make sense. So what they now did here was to say, okay, this value, why these two values are different is that they did a combined system here. So what they did was they added the flow from sewer here, which in our own case, you don't need to add this. So you go directly from here, divided by 0.9. It will simply upscale the value. So what is happening here is simply upscaling. So instead of designing for 730, you're now designing for 820. So it's an added safety factor. Instead of designing for 988, you are now designing for 1,100. And so on and so forth. Okay, then from here, we'll move from column 16. From column 16, 17, we'll now move. The real column is column 13 or 14. Okay, but that's why this one doesn't have any number, because this one is just an upscale thing. And this is what I did in my own. Let me just show you. What I did here was to say, I say factored. Factor. So myself, I use 1.2, which is like divided by 80, by 0.8. I did that on my own. As a designer, I have to play safe. Why did I do this? I did this because most times, they're using trapezoidal channel. So most times, if you are building road, open drain, the problem of open drain sometimes is that when there's overflow, it might lead to hydraulic jump that will damage the road system. And that's something we should always overflow. We should always avoid. We should always avoid this so that when when the water is surcharging in open drain, give room, give a free board, just add value, add extra few millimeters above what's expected, so that I can still accommodate flow beyond your design value. So from here, we're now going to go to our chart. So from column number 16 to 17, we now go to our charts. So A20 you go to a chart. This time around, I don't think we are using PVC pipe, so we'll go and use concrete pipe. So I would suggest you close this chart and go to the chart of 0.1 for concrete pipe. Because for a drain of that size, you cannot tell me you're going to use PVC pipe. It's going to be concrete pipe. So I'm going to use the chart for concrete pipe. So this is the chart for concrete pipe. It's too much. So you can open the chart so that you can see clearly from mine, you can see clearly from yours. So now we have 800, 700, 800, 900, 1,000. So 800 against 5%, like we did last time. So this is 800 against 5%. Somewhere here. So I'm getting 800 mm pipe. 800 mm. Can someone confirm that? For a flow of 800 liters per second against 5%. And the velocity is 1.8. The velocity is 1.8. Are we together?
Yes, please.
So the velocity is, so that's how we came about this 800. Okay. Let me take another one. Which one should I take again? Any other one? Let me take, this one is 800. I don't need to do for Catchment C. Catchment C is 730. So I can just assume 800. As a lazy person I am, I'll just put 730 there. Just put the same thing there. But when I get to Catchment D is about 2,000, which is 2 cubic meter. 2 cubic meter. So I'll go back to the chart. 0.4. I open 0.1 again. Something is wrong. Oh, one, sorry. So I'll go to 2, which is here. Sorry. So this is 2. No, it's not working. Okay, 2 against the same this. I'm assuming the same slope. It could be different, but the idea is for you to know how to read it. So that's about 1.1 millimeter, 1.1 meter, 1.1 meter drain pipe. 1.1 meter drain pipe. So yeah, 1.1 meter drain pipe. Here they got to 1.4.
Hello.
Yes.
Can I just quickly convert that pipe sizing into a rectangular drain?
Yes. But I'll show you another chart to use that will specify every type of drain. But you can do that too. But I've done it and I got the same thing. I don't know if you understand. Area of a circle is pi r square. Equals 800. You now equate, we do for left and right. You get the same thing. Depending on whether you're using rectangular, please do, so that for learning purpose, please do. Thank you, sir. Please do. Then, so that is how you got it. The other things that are here are checks. You know, we assume a velocity of 2. From the chart, we are now seeing the real velocity. So that is what you now list here. So anything after this millimeter, these things are checked. This is what we did in structural design. When you do your reinforcement design, you see provided, you see, how do I put it? Design and provided. For instance, now let me just tell you how all this other one comes. These are checks. So I'm not going to go into that. That's not as consultants that we're not in academia. Now, like my chart, now let me give you one instance now. Some of this chart that we got, we didn't get the number. Like this one now. Let me use this one for example now. This is 800. And we got it somewhere in between. And we assume the worst case. If I now take this 9 straight to the line that I'm using and now come down, I'll get a new value.
Yes.
So that new value now is the provided. What I provided now is for 900 flow.
That's very correct.
But what I designed for was for 800. I don't know if you understand now. You know, we are getting in between 2 pipes. Now we now choose the biggest one. You now read off the new Q. You now get a new Q. Then we assume 2 meters per second. But when we read it out, we got a new Q. So you now do the new Q over the old Q. If it is not between 0.7 and 0.9, you know whether you're over designing or you're under designing.
Very correct.
Because like the last design we did now, we got 200 for certain flow. It was closer to 150 than 200. If I now do the design Q over the real Q, if it's not falling between 0.7 and 0.9, I will redesign that thing. I will choose a smaller, maybe I'll manufacture 175. But the problem now, in all this design we're doing, there's even a bigger problem in the market that pipes are calibrated. Some pipes are not available. That's why when I got 1.25, I know that you cannot see 1.25 pipe in the market. So already you're going to use 150. And it's very common in water reticulation. You can design water reticulation and you see a 65 mm pipe. You cannot see 65 mm in Nigeria. So you end up using 3 inches pipe, which is 75 mm. So they're already, that one is, but then you cannot use 50. It's better use 75 because, as I said, the philosophy of infrastructure design is better to over-design than to under-design. Under-design should never be allowed in pipe network at all. Is a taboo. It shouldn't be. It's better you over-design so that population and development will meet up with it. Then you under-design that even from day one or 20% into the lifespan of the project has failed. And that's what we see in a lot of pipe design. Then there's a manual I saw online, and I used it, and it worked. So I've included it for us. The good thing about the manual is that it included different shape. If you're using trapezoidal system, you don't need to go and start converting. It's from, look at it. It's called Design Chart for Open Channel Flow. It's from FH, US Federal Highway Manual. It's a Federal Highway Manual of the United States. So there are millions of source charts in the market, in the internet. And for me, I've probed quite a number of them, and they are consistent. So these charts can also be used so that I don't need to convert. If my system is hydraulic channel, I can easily use it. So it's also worth reading. It explains some of these things I've been saying. But let me get to where the chart starts. And show us how to use the chart also. Okay. So pipe flow chart. Just hold on. So these are another charts, but this time around, look at the, when you print it, you can, so here is discharge. This is discharge in cubic feet per second. So the first thing you do if you want to use this chart is that you have to do conversion. You know, the Americans, they use imperial. They use imperial units, while we use British standard. So it's the same thing, or you can still keep looking for the one that has British standard. So on this axis is the velocity. Okay, then this is the, okay, yeah, this is for trapezoidal channel. So you measure the velocity, you measure the discharge. You measure the discharge against the slope. So this is the slope here, and this is now, this is the slope. So this is slope. So this is for slope of 0.2, slope of 0.4, slope of 0.7, 0.1, and can you see that they have gotten to 4 and they stopped? Now, I didn't see this before, but I told us that any slope that is more than 4, you assume the value for 4. That is a normal thing in engineering. Because 4, we assume that 4 is a high worst case slope. But there are some slopes that can be more than 4. But assume the one for 4, because the one for 4 will not accommodate them. Okay. So if you get the discharge, you choose the particular one, the particular slope that is that. Then when you read it off, it will give you the depth. The depth of the channel. And the depth of the channel is explained here. Here, both the slope and the side slope and the width. So this one is, why this one? This one is exclusive for a trapezoidal channel that has a fixed base width. This one shows you that the base width has been fixed to 4 inches, which is 1.2 meters. So you're now looking for the depth of flow. Okay. So look at it, say channel chart, base width 4 feet, and the slope of the vertical to the horizontal has to be 2.1. If you go down, you see other charts that have different calibration. This other one is for the base width that is 5 feet. So what is this telling us? What it's telling us basically is that if you are using trapezoidal channel, you must fix one end. Show my screen. Okay. You must fix, okay, thank you, Bila, Baba. Okay, so you must fix one end. So if you are fixed, if I use a trapezoidal section, and you have fixed that the base width is 5 feet, which is 1.5 meters. You are now looking for the depth. You use this particular chart. If you have fixed it to be less than that, you go up. So this chart is a lesson, is a tutorial on its own, which you cannot accommodate in these 3 days we have, but you have the material. And this one is the one that the base is 2 feet, that means 600. I think this is the number one they use in many estates. I know that they always fix their width as 2. Then the upper one can be, if this is 2:1, that means the upper one will be 4 feet. Will be about 4 feet. Then the depth now is what you read off from here. And that is based on the discharge, based on the slope. Look at the slope, 0.05. Now this slope now is not like our slope that is calibrated per mil. This slope is dimensionless. Can we see the slope, gentlemen and ladies? You see the slope now is calibrated. So that our slope that is 5% is about here. This is 0.005. Multiply this by 1,000, you get, no, sorry, this one, 0.05. This is the slope we'll be using in our from the Colebrook chart. But in the US Federal Highway Manual chart, this is their own slope. So if my discharge, one of our discharge was 15, one of our discharge was 15. So what I'll do here now, if you are still with me, I'll come to 15, I'll go up until I meet 0.05. And this one is telling me that it is the depth is 1 meter. So this now becomes 1 meter deep drain over base width of 600. So if I do the vertical over horizontal 1/2, I can get the top width. So the base width now is 0.6 meters. And the vertical width, this trapezoidal channel is 1 meter. Okay, therefore, if you do your Pythagoras well, the up width will be around 1.4 or so. So that becomes the equivalent section for a trapezoidal section, whereas the other one will give you a circular section. So the another thing about this chart now is that this chart can only be used for a trapezoidal member, while the Colebrook chart I showed us can only be used for a circular member. So if there's another type of member, rectangular member you want to use, it's also here. It's here. If you go up, if you study this chart, it's here. You see for the rectangular. Then if you can't find it in my material, please, as an engineer, just Google online. You see hundreds of them. All you need to do is that anyone you adapt, understand the rules of using them. This is pipe, the same pipe we use. If I go further up, I will definitely get one for rectangular section. So one of the things some of us might have to do is to compare the value in this chart with the value in the circular one. I can tell you, and I can bet my bulbs, you're going to get the same answer. It just depends on using American chart and you're using European chart. In fact, not even European chart. This chart was developed by the University of Stuttgart. That's why they customized it. They have a big institute called the Institute of Sanitary Engineering, a big institute that services the region of Stuttgart called Baden-Württemberg. You know, unlike what we do in Nigeria, everywhere that a university is instituted, the lecturers and the professor will constitute themselves into a team of consultants to be servicing the infrastructure of that area. Like in Abuja now, some top engineers in Abuja will come together, form Abuja Engineering something, and will be the one managing WUPA, managing Lower Usman Dam, managing everything infrastructure. And so we can be able to stay synergized with the University of Abuja and come up with some standards, some codes, and some things that we know that are unique to Abuja. And that's how things are really done in some countries and create value for their engineers. Okay, please, let's ask questions. Question time. He said, can we decide to use any particular shape of drain? Yes, you can use, but your job will be to find the chart that incorporates that drain, that shape. For now, we have used 3 shapes: circular, trapezoidal, and I was trying to show us rectangular, but rectangular is here. Somebody should probe this chart. You see rectangular inside, and I've given to us. Then if you go online, unfortunately we can't read Chinese. I know Chinese will have hundreds and thousands of them, but then how to read their language will be a difficult thing. So for the English-speaking countries, you see a lot of charts online, and you can use any of them, provided that you understand the rules guiding those charts. Okay. Okay. Any question, please?
I think we are closing for today.
Yes, but not without asking questions or able to telling me you're okay, that you've gotten everything. Or unless you ask me to allow you to go and go through it, because most training is not that you grab everything from day one. If you grab anything from day one, then I mean, what's the sense? So, but when you go through these things, it will begin to make sense.
Yeah. Yes, we will go through them.
So tomorrow I will just be introducing us on how to use SWIM, Stormwater Management Model. we'll just do a small tutorial there, which somebody can capture. We can capture, okay, how do we generate the catchments? Page 2. How do you generate the catchment? Please, can you on your mic and ask me, Sikema, how do you generate the catchment? The catchment will come from the developer. They must have done the route survey. They must have done the survey, and maybe you can propose it with an area map.
For me, it appears academic still, because one, you've been given all the information you need to do your job.
Okay.
But if you go on the more practical side of things, where you have maybe drawings speaking with you, now how do you really map out all those?
Okay, look at it. Look at this one. This is a district, one of the outskirts in Abuja, one of the satellite towns in Abuja. So this was given in AutoCAD. Can you see my screen?
Yeah, I can.
This was given in AutoCAD. It's a big district. So what we did now was to use this district was given. Then watch me, just stay with me. I divided them into this catchment. Now I can tell you that this my catchment is a lazy man catchment. There should be more than this, but I used experience. I divided them into, I make sure that none of them is above 5 hectares. Hello?
Yeah, I'm with you.
I make sure that none of them is more than 5 hectares.
So hello, sir.
Sir.
I want to ask, is it the polyline approach you used?
I don't know approach polyline, but what I did was to know which catchments fall within the same slope area and within the same stream flow. Unfortunately,
okay,
I cannot.
So you just traced.
Trace, thank you. I cannot open the AutoCAD file here because it's too heavy, but there are some streamlines. I don't know how to explain to you. There are some streamlines that I know that this person cannot flow into this one. It's a critical thing to do.
Hello.
Yes.
Yes. I suppose that we should do this. There's some other software that can use to do all these kinds of like.
Who can hear you, sir? Hello, sir.
Or some things to do catchment.
Yes. We can't hear you, sir.
Hello. Okay.
We can hear you now.
Okay. The way actually, for example, is a surveyor's work. When a surveyor will go to the site, it will take the elevation and the spot height of the area. The surveyor will divide them into different seawasheds. When you break them, any portion that will drain to a particular area, due to the slope of the area. So the surveyor will now have to demarcate that specific area. So because of that, you cannot have your different catchments that you are now zoning based on the slope, based on where they are draining to. So from there, you can easily, because all the water flowing within a particular seawash must be able to have a common outfall. So the surveyor will demarcate. The one we did in Lagos, the surveyor did it everything for us like a map, and I sent it. So you can just upload the map into the software, and digitize and get your own network.
Okay, that's from another perspective. Somebody was trying to say something, but we didn't hear him well. Somebody was talking something about Civil 3D.
I'm saying, yeah, we don't. Surveyor don't do things like that for us. The engineers, we do it by ourselves, you know.
Okay.
And there are softwares that you can use for that too. You can use Runoff, for example. You can use ArcGIS.
Okay.
ArcGIS will do it.
Yeah, you know. You can use, you know, you can even use 3D. There are ways to use 3D too. So there's a lot of stuff to do, but
even DM yes. Will do it.
They don't do it for us.
Yes. These are tools of surveyors. The surveyor use GIS, they use digital elevation model, and they use all those. Ideally, surveyor give a perfect information than engineer. So we only try to use survey-based map on Civil 3D and GIS. So when you even link them, for example, the advantage of Civil 3D, when you even link up Civil 3D with Civil 3D SSA, there is a Civil 3D SSA, you link it all with Civil 3D. So anything you do in Civil 3D, the advantage of Civil 3D is that anything you do in Civil 3D, when you link it up with SSA, you only just come and update. Any changes, you just come and click update. Everything will just be synchronized together at the same time. But that way, those Civil 3D, that SSA is beyond the level of this class.
Anyway, I want to agree with you on that actually, because at the end of the day, the base source, the base data that I use to do all those stuff are still from survey, topographical survey.
Yes.
It's true.
Can I say it depends on the quality of the surveyor.
Yes, you can see that too. You can see that too.
Quality of survey data. It's depends on quality of survey. As in to make it easy, but we're all saying the same thing. But what I'm saying is some surveyors might not be able to do it based on limiting factor they have. So in that case, that's why we now have to call in softwares. Also use experience. If you are looking at an elevation, you'll be seeing the grade. You'll be seeing the if you are taking the spot height very well, you'll be like this one. Well, by tomorrow, one would use a panel to do this because what's on they just mentioned now, as I said before, there was no SSA until 2015 or so, or 2013. But swim have been around for the past 30 years. And the last time we went to Germany, I found out that what they've been doing these days is that when they go and use the back end of some of these old softwares, they will now create a DWG interface. So tomorrow, when we introduce the swim software, some of us, like I use swim to do this, to subcatchmentalize some of them and bring them into small catchment area and then get their flows. Okay, any other input, please? I think our time is fast spent.
Yes. We're tired.
Yeah. So, gentlemen, let's we'll go into the day. Tomorrow I think we've practically done what we need to do in this course. But just tomorrow, we just have to introduce the concept of software, how you can use the software and do some few simple things. So for the software, it's going to be an introduction, how to use these tools. Then on our own, we can go further, go deeper, and play around with it. But the software has limited use when it comes to the real thing we're doing. What we're doing, the real thing we're doing is what we have done today. Okay.
Thank you very much, sir. Thank you.
Yeah. So please, what else? I shared it. Hello?
You said you're going to share it because I've not seen it actually. I don't know if anybody got it.
Which one?
This particular, is it the Stormwater network? Is this particular one on your screen?
Okay, this one. Okay, tomorrow I'll share it tomorrow. I will just move the name of the thing and yeah, it's somebody's work, so I'll remove it. I'll share it. Okay.
Okay, thanks, guys. See you tomorrow.
All right, sir. So we'll see you tomorrow.
All right, sir. Thank you very much. We appreciate.
Thank you.
Thank you, sir. Good night.
All right, good night.
Thank you, sir. Good night, sir.
Engineer, where are you?